How you doing? So we're going to take a look at section 10.3, which is on geometry. We're going to focus on the mathematics of perimeter primarily. We're going to touch a little bit on something called a tessellation. Now that part is more for your projects that you might want to be working on than anything else. But kind of this will be a short unit on not permutations, that comes later, perimeter. Here we are. So, chapter 10, geometry. Interesting. I gotta click over here. There we go. Now we can change the slide. So polygons, perimeters, and tessellations. So we'll talk a little bit about polygons to start with, so then you can have an understanding. But our primary concern tonight is going to be about finding perimeters, the distance around an object. So a polygon is any closed shape, which means that it has a beginning, and the beginning and end come back together. So you got a starting point, you do something, and it's closed if they meet up again. A regular polygon has sides which are all the same size, length, and the angles are all the same measure. So we'll take a look at regular polygons, but then there's also non-regular polygons, kind of like what I drew. This would be a polygon, but a non-regular one. Okay, but in either case, any polygon, the perimeter is the sum of the sides, which means we just add the sides together. So looking at our regular polygons, we've got triangles which have 3 sides. So you see the Latin for 3, tri. Quadrilateral, which means 4. Quad is 4 in Latin, 4 sides. And if it's regular, we also call it a square. A regular quadrilateral is a square. Pentagon, hexagon, 6 sides. And again, if you have taken any Latin, you know these prefixes: a heptagon, meaning 7 sides, followed by the octagon of 8 sides. And we can keep going on these, but usually much above this we'll just refer to it as a 9-sided polygon. There are words you could use for it, but we'll stick with those. Okay. The types of quadrilaterals. So these are, remember, quadrilaterals are things that have 4 sides. We will be looking at area, volume, and later in the next unit. So that's why we need to understand these a little bit. So again, the square is the regular quadrilateral. If it's a regular quadrilateral, each of the angles is going to be 90 degrees, as indicated here, and each of the sides is equal. It's the only regular quadrilateral. The other quadrilaterals, there's a rectangle, which 2 of the sides are longer than the other 2, so it's kind of like a stretched out square, if you want. A rhombus, all the sides are equal, but the angles are not, so it's been kind of a squished down square, if you want to think of it that way. So it's not regular because the angles are different. And then a parallelogram is like a rectangle. It actually is, the rectangle is a special case of a parallelogram, but a parallelogram, the angles are not all 90 degrees. It's been squashed down as well. So kind of a squashed down box. So parallelogram, rhombus, rectangle, squares. And then a trapezoid is the one where it doesn't have equal sides. Actually, you've got 2 sides that generally are going to be equal, 2 sides that are parallel, but it gives us sort of 2 bases, a top and a bottom. We're going to take a look at trapezoids a little bit later when we get into 10.4. So let's get into finding perimeter. one problem with, or a question, is we're going to look at how much it would cost to put a fence around a field. And we're told that one side is 42 yards, the other side is 28 yards. So since it's a rectangle, I guess they don't really tell us that, but it appears to be a rectangle, so we're going to have to make that assumption. If this longer side's 42 yards, we will know that the top part will be 42 yards. And then if the right-hand side's 28 yards, the left-hand side will be 28 yards. Okay, so find the perimeter. Well, if you were just going to take a walk around your property here, how far would you have to walk? You'd walk 42 yards. Then you'd walk 28 yards. Then you'd go another 42 yards. If you didn't meander like I did. And then you'd go another 28 yards, so you got back to the beginning. So we've got, what did we get? 42 yards plus 28 yards plus 42 plus 28. So if we add all those together, we're going to get 42, the 8 makes that 50, plus 2 more, that's 70. That makes this 70, and 70 are 140 yards. Okay, so we just took a walk around the rectangular field. And we can see here, another way we could have done that is the perimeter formula is 2 times the length plus 2 times the width. I don't particularly care to use these formulas because had this been some other shape, the formulas would be different. Instead of remembering all these formulas, it's sort of easier, better to just go ahead and count as you walk around, count each side or add each side together. It will always work. And the other thing is when we get to area, we need to start using formulas. And I've just seen too many times where people memorize all these formulas and they'll use the perimeter formula at the wrong time. They might use it for area, or they'll use the area formula when they want perimeter. But if you just draw your little dude, walk him around the fence, you'll always get it right. Okay, 140 yards. I tell you, it's going to be short because all we're going to do next is figure out how much does it cost to buy that fencing. And since it's $5.25 per yard, we just need to multiply this by the number of yards that are in the number of feet that are in 140 yards. So there's this ties us back to what we were doing back in chapter 9. So to get the cost, what we first need to do is take our 140 yards and since our unit of price is in foot, we need to convert that to feet. And if you remember, what we did is since we want to get rid of yards, that there are 3 feet in a yard, we want to get rid of the yards, so we divide by yards, and that leaves the 3 feet in the top. Okay. The yards are going to cancel, leaving us 140 times 3, which is 0. 4 times 3 is 12. Carry the 1, 3, 420 feet. So that's how much fencing we need. And then we just need to take our 420 feet and multiply that times $5.25 per foot. So notice how the feet will cancel. Just kind of keep track of your units. 425 times 525. I forgot my calculator, but the good news is we'll let them calculate for us. Okay, so we see the calculation they did, 140 yards, they did the conversion. We've got the 420 feet, basically the same way we did. Then on the cost, 420 feet times 525 per foot, the feet will cancel out. 420 times 525. If we would have had our calculator with us, we would have got the $2,205 for that fence. All right. So that's getting perimeter. You're going to have some other questions in the homework where, again, just add all the sides together and you'll be good to go. So now tessellations. This is remember we did this project that I had you do, is to actually make a tessellation starting with a triangle, and so get those in. That's your project. Let's see how it goes. But a tessellation is a pattern consisting of repeated use of the same geometric figures. And again, your triangle, you funkified it and then you moved it all over the plane. So there were no gaps or overlaps if you did it right. One of the things we didn't talk about, but each vertex where you do the turn has to have a 360 degrees so that it goes all the way around the circle. So we're going to just go ahead and take a look here at some examples of tessellations with, since we talked about polygons. The thing is one of since none of the polygons can fit together except for a square, which would be kind of boring, I guess, a bunch of squares just all next to each other. You can't get tessellations of a polygon by itself. You need two different polygons to make the circular patterns here. And here are some examples. And for those of you looking maybe to do something with this, something artistic with your final project, the math of blank, here's the math behind it. That's why you can't just use like pentagons. There would be something left over. Here's some work by M.C. Escher. And I don't remember what the MC stands for. I think but anyway, M.C. Escher was an artist, mathematician, and he did a lot of tessellations. So here's one with the variation in color, but again, taking that similar shape. Here's one with some lizards interacting with each other. Again, much like you did with your funkified shape, creating this tessellation and artistic look at things. And then there's this other thing he did. This is not a tessellation, but this kind of gets you to the next phase. Escher did a lot of things what he called impossible drawings. Notice the stairs are going up and down at the same time, different directions. And it's a visual, they're playing with your mind. You cannot actually physically do this. And if you're interested in this sort of thing, I've also posted a video in Canvas that's about 12 minutes long, and it talks about this this mathematician who actually constructed some of these. And the thing is the staircases that go up and down and sort of infinite staircases, they can only exist if you get a particular angle. They don't physically actually work. But watch the video if you have an interest, and you'll see another mathematical topic dealing with artistic creation, how you can actually create things that can't physically exist, at least not in our 3 dimensions. So that's our chapter or section 10.3. Go ahead and take a look at the homework. If you have questions, come on in and ask during class time. Thanks.